So let's now see how to create the crystal structure using VESTA software. So we're going to discuss in it two types. First, how to create it from scratch, and second, how to edit the existing zip file, crystallographic files, to edit the data so that we can get our required crystal structure without actually going through the process again from starting. So for here you have to download the VESTA software, which I have already downloaded. Here it is. Now from files you have to go to new structure, and here we are going to discuss about the simple structure cesium chloride, how to make it. So for cesium chloride, here you can rename it to cesium chloride. In this we'll go to unit cell. As we know that cesium chloride is cubic, we'll go to cubic and its space group is BM3 bar M, and its unit cell parameter is it has A, B, C all equal, so it is only asking for one input and it is 4.01 angstrom. Okay, it will give us the crystal system, and now to actually put atoms in it we have to go to edit the data, unit cell. uh, okay, we have already done it. Now structural parameters, new, we have to add the symbol. Let us add for cesium and label it cesium. The charges +1, and the coordinate is 0.5.5. It is actually present at the cubical void formed by 4 chloride atom present in the corners forming SEC, and the cubical void happens to be at the center of the unit cell. So okay, we'll click apply. Now new, which is chloride atom making the SEC, here it is, and we'll label it as chloride. The charge is -1. Okay, and the parameter, it is present at the unit cell corners. So it is present on the corners of the unit cell as we have discussed, and we'll click apply to see the atoms. Okay, everything is good. Okay, apply. Okay, so here you can see all the details, what you did till now, all the lattice parameters, all the angles, the unit cell volume, etc. You can see all this information, and you have created a unit cell of cesium chloride from starting. Okay, now for actually drawing the crystal systems that was given to us as the part of assignment, um, we can create it by editing the parameters in the zip file which is already given to us. This is the zip file, crystallographic information file of barium titanate, and in the assignment we were given to draw example for rock salt, okay, which have the 6.356 cell parameter. So let's draw for calcium telluride. we can only make changes in the zip file, and then we can open it in VESTA software, and it automatically gives us the unit cell. So starting from here, we have to change the edge length to, which we have discussed, 6.356. Okay. um the cell length is 6.356, 0 0, changing it for below because it is a cubic unit cell, and all ABC's edge lengths are equal. 356 6.356 Now the cell alpha, beta, gamma angles are the same. We can change it to calcium telluride, calcium telluride, calcium 1 atom, telluride 1 atom. Okay, for simplicity we will keep the space group as P1, and the cell volume we can calculate it by taking the cube of this 6.356 into 6.356 into 6.356, which is 256.77436. So rounding off makes 37. Okay, now we just have to change here the fractional coordinates to our required structure to get CIF file for calcium telluride. Now it is given that it forms rock salt structure. For rock salt structure, the cation need to occupy the octahedral void and the anion need to form the FCC lattice. Let's start from anion, which is telluride because it's more electronegative. So telluride will occupy the corners 0 0 0 and the face centers, which is 0.5 0.5 and 0.5. Now if we will discuss about the this becomes an FCC at the corner 0 0 0, at the face center, sorry, it I made it body center, it face center, it becomes 0.5 0.50, another tellurium which is 0.5 0.50 0 0.5 0.5 and another tellurium which is 0.5 0 0.5. Okay, let me check. 0 here, 0 here. Okay, now making all the tellurium atom making the face center, we have already added the fractional coordinate. Now we'll add for calcium. Calcium occupies all the octahedral voids, which means its fractional coordinate should be 0.5 0.5 0.5 and for calcium occupancy is 1.0. We had made one octahedral void, as the cubic cell has how many? 4 octahedral voids, one at body center, and each on 12 edges, and contribution is 4. So 12 divided by 4 gives us 3. So 3 plus 1 gives 4. Okay. So at center wala coordinate, it will be 0 0.5, 0 0 0 0, 0 0.000, 0 0.0000. U ISO um, calcium. Enter another calcium 1.0, 0.5. We have already done that one. 0.00, 0.50000, 0.0000. It will be okay. Give me a second. Okay. Now UISO calcium. Now for the last octahedral void fractional coordinate 1.0, 0.000, and 0 and 0.500. So these three fractional coordinate gives us octahedral void at the edge center, and 0 0.5, 0 0.5, 0.5 gives us the octahedral void at the body center, and at the corner telluride gives us 0 0 0 fractional coordinate, and at each face center it will be 0 0.5, 0 0.50, 0 0.50, 0 0.5, and 0 0.5, 0 0.5, 0.5. Okay. UISO calcium. Let's change the atom notation here also. Tellurium, uh, tellurium, cal sorry, tellurium here too. Tellurium, here is also tellurium, and here is calcium. Okay, so we have made a zip file for calcium telluride on the basis of its rock salt formation like structure, false rock salt like structure. So now we'll save it. File, save as calcium telluride text form, and we'll save it here. Save. Okay, now that we have saved it, we'll go to VESTA file and open the zip file that we have just saved. Um, Solid state zip files. Just a second. File, save. As calcium telluride, we have saved it. So as we have created a new file from the existing zip file for calcium telluride, we'll open it in VESTA. We'll go to file, open, and open the calcium telluride zip file we have just prepared. Open, and it will show us the structure of calcium telluride. Now removing all the extra atoms from this tool, delete, delete, delete. We can zoom out from here to delete, delete. Now we'll change the angle and again delete all the extra atoms, delete, delete. Now from here you can easily see the calcium telluride structure with the telluride forming FCC. We can see the golden atoms are telluride atoms forming the FCC unit cell occupying the corner and the face center, and the blue atom as calcium atoms which occupy the body center, which is here, body center and the face center. Okay, my laser is not working, but you can see here body center, telluride and the face center, sorry, at the edge centers in all the octahedral void. Now I have created in the similar way all the zip files by editing the already existing zip files for different structures, that is gold, Zn, cesium oxide and gallium phosphide, potassium oxide, and from these files I have explained in the next section how we can visualize and conceptualize the atoms that are present in these unit cell by rotating it on all the possible directions occupying different position, like how the atoms occupy a specific position in the crystals that are formed. In these slides, we will learn the crystal structures of different compounds using the software called VESTA. Creating its zip file and uploading it in the software VESTA gives us the crystal structure of different compound. So we will study these in these slides. The calcium telluride forms the crystal structure type of rock salt, which means the cations, which is the calcium ions, they form the octahedral void, which is on the body center and the edge centers, and the anion, which is telluride, forms the FCC lattice, which is the face centered cubic lattice occupying all the corners and the face center of each face. From this video we can see that these blue items, these blue are telluride ions, and these golden color as calcium. They occupy the edge center and the body center, and these telluride ion occupies the corners and the face center of each of the 6 faces. Now for the structure of gallium phosphide, it follows the crystal structure type of zinc blende, which means that the cations occupy alternate tetrahedral voids and the anion makes the FCC lattice, which is the face centered cubic lattice. Now seeing the crystal structure, these green atoms are gallium. The green atom are gallium and the purple atom are phosphorus atoms. So we can see that this corner and these 3 makes a tetrahedral in which the gallium atom is present. Now we can clearly see. So this is present in the tetrahedral void. Now we can see that there is no in the alternate one. Then again gallium is present in below one, there is no gallium, but in the alternate one there is gallium. So of the 8 tetrahedral void, 4 tetrahedral voids are occupied by gallium cations. In this slide we can see the compound potassium oxide, which follows the antifluoride structure, which means that the anion, which is the oxide ion, forms the FCC lattice occupying the corners and the face centers of each face. and the cation occupy the tetrahedral void. Now they occupy all of the tetrahedral void which is present in the crystal structure. So if we take a look at this video rotating the crystal structure, we can see the tetrahedral void being occupied by purple potassium ions and the red oxide ion occupying the corners and the face centers. So in this crystal structure, and now the tetrahedral void, if we consider these red atoms, the three red atoms, like like this, and one at the corner and three at the face center forming a triangle, the tetrahedral void is occupied by this purple ion, and it occupies all the possible tetrahedral void present in the crystal, that is the 8 tetrahedral void present in the crystal. Now if we consider the crystal structure of cerium oxide, it follows the fluoride structure, which means that the cation forms the FCC lattice and the anions occupy all the tetrahedral void. In this crystal system video, we can see how these green atoms, which are the cations, occupy the corners and the face center forming the FCC lattice, and the red atoms, which are the anions, occupying all the tetrahedral voids possible in the crystal structure. And the tetrahedral formed by these three face center again forming a corner, forming the face center, and the corner atom gives the tetrahedral void in which the atom is present, um, which is the anion. For the compound gold and zinc alloy, it follows the crystal structure type of cesium chloride structure, which means that usually the gold act as more electronegative atom and zinc as more electropositive atom. So zinc forms the body center void, and the gold forms the SCC centering, having the atoms at the corners of the unit cell. So in this unit cell we can see that at the corners gold is present, and in the body center zinc is present, and we can see that each zinc atom is touching 8 gold atoms, which means that the coordination number for the zinc atom is 8, as well as if we do unit translation, we can see that the coordination number for the gold will also be 8. That means that each gold atom is surrounded by 8 zinc atoms. So the coordination number ratio becomes 8:8. So in this slide we have learned the actual lattice points of the unit cells following a particular lattice centering that makes the lattice. We have learned the use of software VESTA and making CIF files and uploading in on VESTA, making the crystal structures, and visualization of voids in the crystal structure from every possible angles we have seen. Thank you.